again for giving me this opportunity to present some part of my work related to reinforcing of Benguela upwelling system and associated impacts on primary production. The left-hand right picture is me. Volker is in the middle, and Martin Schmidt. These two guys are my bosses, and they contributed a lot in these presentations. Okay, the outline of this presentation. First, I briefly talk about the terminology we will use in this work. I discussed different drivers of upwelling across different upwelling systems. First, Ekman coastal upwelling as an important or maybe the most important contributor of upwelling. I will move to wind stress curve driven upwelling. Briefly, I will say few words about equatorial upwelling. Ice edge upwelling will be very shortly discussed. Some aspect of submesoscale ocean dynamics and associated upwelling or downwelling will be discussed. I will brief you list different other physical drivers of upwelling. In the second part of my talk, I will stop here in this part and we will discuss, it will be some discussion about the different physical drivers of upwelling. And after that, I will give you some of our ongoing research related to Benguela upwelling system in terms of mean state, variability in the model and Ekman theory, and also some relationship between coastal and offshore upwelling, which might be interested with biologists and ecologists. And at the end, I will summarize my results. Let's get it started. Yeah, the terminology. First, what's the meaning of physical upwelling? In the perspective of physical oceanography, upwelling means when deep water is being brought to the surface with any physical processes and stays in the surface for reasonably good period of time, like several days and so on. This is very simple. Our definition is a bit different from biological upwelling. Another important physical concept is Coriolis effect. When we consider, first of all, Earth is a rotating, if we are standing on the Earth, as Earth is a rotating coordinate, means every observant over the Earth's surface rotating, it is not inertial coordinate. So for the observant standing on the Earth's surface, any parcel of air parcel or water parcel, when it moves for a couple of days, the observant see that this parcel is deflected to either left or light, depending on the hemisphere. It is deflected to the right or left side of the original direction, and it is associated with Coriolis effect. In the northern hemisphere, as we can see in this picture, in the northern hemisphere, let me find zoom, yeah. In the northern hemisphere, when we go, for example, northward, we can see that the movement, it is deflected to the right. Opposite is true for the southern hemisphere. What we should consider regarding the Coriolis effect is that Coriolis effect is maximized in the north and south pole in terms of magnitude, and it is almost zero in the equator. Equator, in other hand, is the place that Coriolis force changes its sign. Coriolis force is involved in any atmospheric or dynamic process which lasts longer than 1 day. regarding the size and the contribution of F or Coriolis force, it depends on the geographical latitude and is shown by this function, which is which is shown here. Also, here, F is proportional to the sine of the phi, and phi is the latitude. And as I mentioned at the beginning, it is almost zero at the equator, right at the equator, and it is maximized in North and South Pole. One important dynamics which is related to different upwelling processes is Ekman dynamics, or is known as Ekman dynamics. During the expedition of Nansen to the North Pole, he realized that the iceberg is somehow they tend to move with some angles with the direction of wind. They are not exactly at the same angle, or they are not moving in the same direction as wind. They make an angle between 20 and 40 degrees. And Ekman discussed this phenomena, this guy here, discuss this phenomena in details with some assumptions. He tries to simplify the motion, and he considered a balance between Coriolis form, the term I just introduced, and the friction associated with wind. He solved the mathematical equation or equation of motions, and he showed that there is, if we consider the direction of wind, there is a kind of rotating or a spiral shape of movement in the water column, which is known as Ekman spiral. What he showed that in his theory, it was that it was very similar to Coriolis force. The net ocean mass transport associated with wind is perpendicular to the wind direction. I mean, if we integrate this Ekman spiral over the water column, it's perpendicular to the wind stress. Or in other hands, in this zonal direction, the move or the water mass transport is proportional to the zonal component or the y component of the wind stress, and vice versa for the meridional component of mass transport. One classical view of Ekman transport was the wind-driven coastal upwelling. When the wind is parallel to the coast, the surface water, according to Ekman dynamic, pushes either away or toward the coastline. When the water is pushed away, the water should be replaced from the subsurface water. And this brings cold and nutrient-rich water from subsurface to the surface. This mechanism is associated with declining sea level or stressing sea level near the coast. Another kind of geostrophic balance is formed, which is associated with very strong or swift current known as coastal jets. Coastal jets are typically in the order of 2 or 5, between 2 and 5 meters per second in terms of velocity. As I mentioned before, this upwelling is associated with cold and nutrient-enriched water, which is brought to the surface and facilitates the growth of phytoplanktons and microorganisms. It brings a lot of nutrients and organic matters to the surface. One important aspect of this mechanism is that a special fronts here is formed associated with jets, And these jets and associated SST fronts or fronts in general sometimes becomes unstable and break into mesoscale and sub-mesoscale dynamics, which will be discussed later. Coastal upwelling index. Coastal upwelling index is shown that according to the Ekman dynamics, is shown that is proportional to the alongshore wind stress and F, which is Coriolis form. Coriolis form it plays very important role in this respect that when we are close to the equator, as you can see, first F is in the denominator. I mean, this mass flux is proportional to the inverse of F. It means when we are close to the equator, the impacts of wind is stronger in terms of mass flux and upwelling, which is the case for Peruvian upwelling system. Yeah, moving to the next slide. Some aspects of upwelling is very interesting in this respect that over the eastern boundary, when we have kind of quasi-permanent equator-ward wind, this wind is more or less parallel to the coast or alongshore winds associated with different high-pressure systems. This high-pressure system, which is known as anti-cyclonic system for the meteorologists, in the northern hemisphere are associated with clockwise motion, and in the south associated with anti-clockwise. And as you can see, in both hemispheres, they are associated with equator-ward winds along the coast. And these are more or less persistent through the year or year-round wind. That's why these upwelling systems are quasi-permanent upwelling systems. In left-hand side panel shows the pattern of the wind in JJA, and in JJA means June, July, August, and in the right-hand side panel, it's the same for December, January, and February. And as you can see, the pattern of the wind is more or less the same over the eastern boundary. An eastern boundary known as California current system, Humboldt current system, Benguela upwelling system, and Canary current system. In the bottom panel, you can see the chlorophyll A concentration, which can be considered as the indirect measure of surface primary production. You can see this is particularly high over the eastern boundary system, meaning the impact of physical upwelling on the primary production in the system. Now I move to this part, seasonal upwelling. There are some upwelling in the Earth climate system which are not permanent, but they are seasonal, like the upwelling in the northwestern part of Indian Ocean or Arabian Sea here, which is associated with monsoon. The monsoon, if we consider the monsoon here, we have a longshore northward wind, and this associated with a strong upwelling and primary production. Other systems are known, for example, in southeastern part of Australian continent, near Tasmania and southwest sector of Australia, near Sumatra in South China Sea, in northern part of Australia near equator, Papua upwelling system. Those are examples of seasonal upwelling system which are basically associated with alongshore winds. Some important features of the upwelling system was to be discussed. First, this is a question whether any kinds of upwelling or any kinds of alongshore wind can create the same level of primary production or the same impacts on the dynamics of the ocean and so on. One important aspect is the timing of this upwelling. How long is the upwelling is quite important. If the upwelling is, if the upwelling is longer or the upwelling event is longer than special time, the water or subsurface water from the density interface can reach the surface. It's called fully developed upwelling or full upwelling. And this time can be approximated with the time that upwelled water is needed to reach the surface. Based on this relationship, this is R is the Rossby radius of the formation, H is the depth, and UI is the index of upwelling I introduced before. And R is related to the gravity and the density difference between density interfaces. And of course, F is large near the equator and small near the pole or other mid-latitudes. For example, if we consider R 5 kilometer and H 100 meter, for 1 meter is 1 square meter per second of coastal upwelling, delta T is equal 5 or 6 days. It means if the wind is continuously blown over the sea surface, after 5 days, the water from the subsurface can reach the surface. Otherwise, if the vertical velocity is weaker or the duration is smaller than that, the cold water cannot reach the surface, and it's called partial upwelling. One of the consequences of the upwelling, of full upwelling, is that when the water here, when the cold water reach the surface, here the water is basically denser than the water or the ambient water, and colder than the ambient water. It has some impacts on the system. First of all, there is the SST gradient. Here the water is colder than here. It will further intensify the local wind. And this is associated with the breaking because it brings new instability in the system, and it is most of the time associated with the formation of mesoscale and submesoscale dynamics. And in terms of biology, this is kind of mature phase of upwelling compared to the partial upwelling, where the cold and enriched water cannot reach the surface. And now some important or some interesting aspects of the upwelling. First is rate of upwelling. Why the rate of upwelling, or why the magnitude of velocity is important? When the rate of upwelling is high, like in the case of near the coast upwelling here, it brings high nutrients to the surface. This high nutrient environment or rich nutrient environment is favorable for bigger phytoplankton cells like diatoms. Why? And at the same time, when the rate is smaller, like further offshore, rate of upwelling is smaller. It brings less nutrient to the surface, which is favorable conditions for small microorganisms. They have larger surface to volume ratio, and they are more adaptable to nutrient limited environment. They can compete better. For the duration of upwelling, this is also another importance for the biologists, because sometimes upwelling is strong, but at the same time, it's associated with a strong offshore movement, offshore transport. Then the retention time is very short. I mean, the nutrient can reach the surface, but at the same time, planktons doesn't have enough time to use these nutrients, to use this environment. It should be kind of balanced between duration and rate. This,
Hadi,
yes.
Hadi, you have 2 more minutes.
Yeah. These two, yeah. As I mentioned, this part will take longer, and the second part shorter, because I thought, yeah, it's good not to interrupt in the middle of different aspects of upwelling. I mean, what I said is well summarized in this figure. Shows the moderate rate of upwelling associated with long duration, or some intermittent upwelling provide ultimate contamination for large fisheries. Coastal upwelling, other aspects of coastal upwelling, it enhances biological productivity. In terms of effectiveness of upwelling for biologists, it depends on the property of shelf bottom waters. As I mentioned, this is upwelling system can be better identified for warmer ocean, because in the warmer ocean the temperature drops with depth rapidly compared to cold ocean. So the upwelling bring cold water easily to the surface, and due to the SST contrast, it can be easily already identified. Upwelling also alters local weather, because, as I mentioned, it brings local intensification of wind, and usually upwelling tend to have fog, mist, and stable condition with a little bit convective activities and little rain. Another aspect of the upwelling is the upwelling associated with wind stress scale. In wind stress scale, imagine we have Ekman transport, but we have divergence of Ekman transport. So the water, due to the divergence here in the center of this divergence, the water or the transported water should be replaced from the bottom water, and it's associated with decreasing sea level and shoaling thermocline and upwelling motions. And the opposite true when these convergence of upwelling, convergence of Ekman transport happen, which is associated with Ekman pumping or downwelling. We can show that this component of upwelling is proportional to the curl or rotation of wind stress. Sorry. Another important mechanisms in the equatorial ocean is called tropical or equatorial upwelling. This upwelling is mainly related to the fact that the sign of Coriolis parameter changes over the equator. It means associated with trade winds in both north and south hemisphere, the mass water transport is moving away from the equator, and the water here should be compensated from the subsurface layer. Good example of that is the SST or cold SST tongue over the tropical Pacific, which is which shows here, and the temperature difference between this area and Western tropical Pacific is of about 10 degrees. We can see here, this is associated with large primary production over equatorial Pacific. Another types of upwelling, which is quite interesting, is ice edge upwelling. The impacts of the wind on the current on that part of the on this part of the on this part which is covered by ice is damping because it's covered by ice. Why? The impact over the free side is the same. So there is a divergent here because the water is moved away from the ice edge and the water from below should be compensated. This is ice edge upwelling. As I mentioned before, coastal upwelling, coastal jets typically becomes dynamically unstable when the SSD gradient is large, and they break up into a kind of turbulent field and form mesoscale or submesoscale eddies. Submesoscales are circular or rotational pathways. When the center is associated with low pressure, it's called cyclonic, and for low pressure means it's associated with the suppressing sea level. So the water, again, they convert the divergence of the flow happen. And I should mention here that submesoscale and mesoscale dynamics, they are in geostrophic balance. Okay, so the water here, the water which moved away from the center should be compensated from below and the upwelling forms. And in this way, cyclonic eddies are always associated with upwelling. And again, the mirror like happened for anticyclonic eddies, which are associated with downwelling. Fully development of mesoscales can lead to a typical form of filaments, which they are a pathway to the ocean interior. Yeah, these pathways advected a lot of water, a lot of cold water to the ocean interior. In this figure, we can see the impacts of filaments and associated primary production, which moved offshore. There are those types of upwelling that I just mentioned, or just described, they are not exclusive drivers of upwelling. There are different types of upwelling in the ocean or in marginal seas, like the interaction between flow topographies, as shown here, can bring upwelling, can induce upwelling, or coastal geometry due to the orientation of the coast. When the alongshore current pass nearby, it can induce upwelling. Tidal motion and tidally induced current can also bring upwelling. Another thing, it's upwelling in the wake of islands. In the lee side of the island, there are two rotating system, eddy system, but which is not in geostrophic balance forms, and they have very strong upwelling. And sometimes we can see near the islands large primary production and nutrients in the surface. Another mechanisms that can influence coastal the upwelling is the propagation of the coastally trapped waves. This can be associated with changing of the local wind, or it can travel long distance from equator. When these waves pass in upwelling systems, sometimes they can fully shut down the upwelling in this region, or they can alternatively they can induce some upwelling. Mixing and internal waves. This is another drivers of upwelling. When we have very strong mixing, and when this mixing is associated with internal waves, the internal waves brings cold water to the surface, which mix up with the ambient water. Okay, with that, I think I would like to stop here and discuss, yeah, about this material I just presented.
Thank you so much, Hadi, for your presentation. It was a very comprehensive overview of different kinds of upwelling systems and a good summarize of all the drivers.
Oh, thanks for your feedback, Natalia. But if something was not clear or was not sufficiently explained, yeah, I would be happy to hear. Yeah, any tips, recommendations, suggestions. Yeah.
I guess the stage is open for questions. So if someone has a question, also the panelist this week, I think is Chris Bartolome. Maybe he has some questions. Otherwise, everyone can either raise the hand or just go ahead and... Chibo has a question.
Yeah, sure.
Go.
Can you go back to the slide where you were talking about the rate of upwelling and how it affects the phytoplankton size?
Yeah, sure. This one, yeah.
Yeah, now did they only look at the size or did they look at the species? Because diatoms have have faster growth rates than dinoflagellates.
Oh, that's a valid point. This is very interesting thing. What it was discussed in this work was related not to the species, but related to the primary production and fishery. And sometimes,
okay.
yeah, and sometimes it's quite interesting. I think I will cover part of your questions in the next presentation. I mean, near the coast, sometimes the coastal upwelling is very strong, then it's a nice environment for dieters because their demands for food is high, and it's a right or favorable environment for them to grow. But it's not the case always, because sometimes the upwelling breaks down and it's the same, and it breaks down and remains the same for a couple of days or weeks. That's why the condition is favorable for a small species, which, to best of my knowledge, some of them they are considered as opportunist species. They can come and become dominant. And I'm not a biologist. This is some information that I learned from biologists in our interdisciplinary project. Yeah.
Okay, thanks.
Yeah, you're welcome.
Okay, so it seems that Kurt has another question.
Yes, Hadi, thank you for this very comprehensive presentation of what upwelling really is. Never heard it in such a beautiful way. And I believe I understand it now even.
Now, thanks for your feedback, Kurt.
Now, my question is the following. Along Brazil and Argentina, there are also surface currents, right, from the north to the south.
Yes.
And there must be no upwelling there. But the Brazilians claim that they do have upwelling. What kind of upwelling could that be?
That's very interesting questions. Associated with, if you look at I read a paper about that first, and they suggested two or three mechanisms which can cause upwelling. First of all, imagine this is the curvature of the coastline, and when the current passes, is associated with changing, and sometimes, as I mentioned, some divergence or convergence happens, and the water should be uplifted to compensate. This is the case we see, for example, near the island. Sometimes near the islands, when there is a current, the current comes, reach the islands, but on the backside of this island, yeah, two kind of eddies form, which these eddies are associated with upwelling. They are not directly associated with Ekman upwelling, but they are induced by this current. And the second thing, the topographic impact. Sometimes the topographic, sometimes we have kind of canyon there, and this canyon is associated, can cause secondary upwelling.
Okay.
This is two things that I read in this paper about the Brazilian upwelling and Argentinian. Maybe there are other drivers of upwelling which currently I'm not aware of. It was to the best of my knowledge.
Yeah, thank you. That's right, that topography plays a very important role in the movement of water masses close to the coast. We have different phenomena also, like internal waves that happen because topography. So it's very interesting, yeah, phenomenon.
Yeah, thank you.
It seems that Chivo still has the hand raised, or is a new question?
Sorry,
perhaps.
I put my hand down. I forgot.
Oh, okay, yeah.
But Kurt does have a second question.
Aha, all
Yeah,
right,
sure.
go ahead.
Okay. Could you illustrate to me examples of cyclonic and anticyclonic eddies?
Yeah, in the ocean.
In the ocean, yes.
Yeah, sure. Unfortunately, the animations I don't have. They are rotating. Yeah, just a moment. I think I have animation for that. Whether I can find it.
I'm mostly interested in an example. Where does this happen in the ocean, and what are the consequences?
Yes, this happens where we have front. There are different mechanisms. First, front and shear instability. When the velocity, the horizontal velocity between the environment, the shear or the difference between velocity is large, like Agulhas current. It's a very good example. Agulhas current is that two different of the water masses meet, and there is a shear in the current, horizontal shear. That's why this mesoscale forms. This is a good example. And for cyclonic eddies, they are rotating clockwise in southern hemisphere. And they usually, when they are clockwise, you can see in the satellite altimetry records, in the models, that this cyclonic motion associated with sea level decline in the middle. Sea level drop for a couple of 10 centimeters. Or in order of 10 centimeters and so on.
Okay.
I don't know, I could clarify that, or I have one animation, and unfortunately I don't know where I save it.
Yeah, it seems that Russell Stevens has also something to add. He posted on the chat YouTube link.
I can just, I started it. It's the Perpetual Ocean, done by Sarah Schrölinger with NOAA's staff. A lovely teaching device that one can use.
Okay, yeah, that's great. I mean, near, for example, Gulf Stream, you can see shear instability around that because the difference between velocity is large, and it's a good environment for the formation of eddies. Or in the Gulf of Mexico.
Perfect, yeah.
If we go to Agulhas region, also here, associated with Brazilian current, North Brazilian current. Yes, this is Agulhas current. This is Agulhas, known as Agulhas ring.
Nice.
Very nice.